All right, so we're going to go ahead and get started with the talk. As you can see, the title of the talk is HTTP2 and what it means for the Java ecosystem. And in particular, this is really about a Servlet 4 talk. Servlet 4, as you may know, is actually one of the key changes that were introduced in Java 8. There are a lot of other changes. If you want to know a bit more about all of the changes in Java 8, I have a session tomorrow. This session is principally focused on just this one change, namely servlets. Skip over the slide. So before we get into servlets and HTTP2, it's important to understand what HTTP2 is trying to accomplish. So HTTP2 is a really long time in the making. It took about 15 years to develop from HTTP 1.1 to HTTP 2.0. And there are a lot of changes that have happened in the world between then and now. And in order to understand what actually happened, you need to kind of turn the clock back and think back about how the world looked like in the HTTP 1.1 and 1.0 world. So, can anybody tell me what this is? A brave person? What's on the screen at the moment? Netscape Navigator, a bit more? Mosaic, thank you very much. This is NSA Mosaic, which is the first web browser in the world. And this is the same time period when HTTP 1.1 and HTTP 1.0 were being developed. So the web of that world looked very much like this Mosaic world. Okay, so in terms of today's world, you have to visualize and think about your typical Wikipedia page, perhaps. Right? So this is how a page looks like. It has a lot of text in it. Some markup, as you can see, a little bit of bolding here and there, a little bit of highlights here and there, maybe a few embedded images, but mostly not. And what you have is hyperlinks. So the HTTP 1.1 protocol is designed and optimized for this particular world. So in this world, fundamentally what happens is that you make a single request, and that is usually a GET request in that URL. And you get a single response back. And the single response is basically encapsulating 80 to 90% of what the web page is actually supposed to render, right? So the basic assumption of one request and one response as a unit made a lot of sense in the HTTP 1.1 world. Now fast forward in today's world, right? So in today's world, when you open up a typical website on a typical browser, this is how your website is actually going to look like. That's fundamentally different from the basic assumptions made in HTTP 1.1. The most important assumption that is being broken is the fact that a web page is no longer just a matter of simply getting one resource and rendering that resource. In fact, on average, if you look at the statistics, some of the data that companies like Google put out, on an average web page, you actually have 40 different resources that are being loaded. So in fact, what's happening is that in order to meaningfully render a page using HTTP 1.1, what actually happens is the browser is making 41 different requests, distinct resource requests, before it can meaningfully render a page. Obviously, this is very, very wasteful, and we'll talk about why this is wasteful in a second. So, what HTTP2 fundamentally is about is taking stock of this new reality and adopting the HTTP protocol to optimize to use this world as opposed to the world in the past. So let's talk about other than the obvious wastefulness of HTTP 1.1, let's dig in a bit more detail as to what some of the fundamental problems with these broken assumptions are. If you were to graph out the resource and interactions between a client and a server, it would look something like this. Right? So you initially get your index.html, and you get a response back of your index.html. You parse the index.html and you figure out, okay, well, these are all of the subsequent resources that I must need to make. So a few different style sheets, perhaps some JavaScript, perhaps some images. In addition to the fact that these are multiple wasteful resources, there's actually yet another problem that happens in HTTP 1.1, and that is called HTTP pipelining or head-of-line blocking. Okay? So, in addition to making these distinct resources, HTTP 1.1 also mandates that these distinct requests are serviced in sequence. Okay, so serviced in the order that the server receives them. The problem with that is what happens when you have a resource bottleneck. Okay, so let's say style 1 and style 2 render quite fast, and that's okay. But style 2 similarly is a fast loading resource. However, it cannot load because you have to load script 1 first. And script 1 happens to be something that loads very, very slowly. Okay? So in addition to the wasteful resources in terms of TCP/IP connections, you also will have a bottleneck whenever you introduce any latency on any cycles of the processing. Okay? In addition to that, to make things even worse, HTTP 1.1 by convention also comes with limitations on how many concurrent requests a browser can make to a particular server. Okay? And that number is somewhere around 4 requests. All right? And this is something called socket abuse or max connections. So if you have that limitation, one way of enhancing your performance is to simply break out your application into distinct parts. Okay? So that you can load resource A through B from one server, resource B through C on another server, and so on. So it's a way of defeating that max connection limit that exists between a client and a server. Okay? So this is yet another shortcoming of a HTTP 1.1 protocol that people have sort of worked around. And there's actually a number of these. It doesn't just stop there. So these are some of the techniques that people use in order to get around the inefficiencies of the HTTP protocol. So these are things like file concatenation and image sprites. So in other words, in order to defeat this limitation of HTTP 1.1 or having to load each image, each resource, one by one, what you can do is you can concatenate all of your images in one large image, and you can load up sprites of that image, parts of that image in your web page. And that's called file concatenation and image sprites. Another technique that's used is domain sharding, the one that I already talked about. So break up your application into multiple subdomains and load up static resources from these various subdomains. Yet another one is called inline assets, and it's similar to sort of image sprites and file concatenation. So let's say you have 5 different CSS files or 5 different JavaScript files that your web page depends upon. So what you can do is you can concatenate all of those things together, and in fact, to make matters worse, encode and compress them and load up all of those resources at once. Okay? So HTTP 2.0, as I mentioned, is a recognition of all these problems and recognition of all these workarounds and learning from these things that people have been doing for so many years and figuring out fundamentally what exactly needs to change in the HTTP world to not have to do these things and to actually fit the web model that we have today. The problem, though, is that HTTP is an extremely pervasive protocol. Okay, literally, the entire world depends on HTTP to work. In particular, older servers and older browsers still need to not break once we move out from HTTP 1.1 into HTTP 2.0. So how do you make these sorts of fundamental changes in the protocol without having everything break? Well, the answer is very simple, and it's actually relatively obvious. And that is something that we do all the time, right? So we as developers use a technique called abstraction to solve this problem. So if you have an interface, right, and your client interacts with you using this interface, well, you can change the implementation, right, and everything will still work. So this is basically the exact technique that was applied in HTTP 1.1. So fundamentally, what happens is that the protocol at a high level, at the API level, the way the browser and a server understands it look very much the same. So if you open up an HTTP 1.1 request and you open up an HTTP 2.0 request, it will look virtually identical. And all of the changes really are at the protocol level. Okay, so we'll talk about what specifically those protocol level changes are that do not touch the actual fundamental HTTP API. So the first and most obvious one is to treat the network and network sockets as a precious resource. So if you're making 41 different requests between a single atomic transaction between a client and a server, well, the first thing optimization you can do is compress all of those and reuse the same connection, okay, to do that. So that's fundamental change number one, is to treat the sockets as a precious resource and to do not just many different connections, but limit the connection between a browser and a server to a single one. Now this should scare you, right? So we talked about, how are you now going to load up all of these 41 resources using a single connection? Well, the answer again is actually right under our noses, right? So we don't have to follow this particular paradigm anymore. This was the paradigm of yesterday. The paradigm of HTTP 2.1 is this, okay? So what you have here in this model is sharing a single connection. So just because you have a single connection does not mean that the single connection needs to just transact over a single request and resource. You can essentially reuse that connection to make multiple requests and responses. And in fact, you're not even limited to making those responses in a sequential fashion. You can actually make those resource requests in a parallel fashion using a relatively old technique essentially called multiplexing. Okay, so what is this thing called multiplexing? We'll talk about that in a second. But these are basically the sum total of the changes that are in HTTP 2.0 that make all of this happen. The most important one is the request and request multiplexing. That's the key change. But other than that, you also have binary framing, stream prioritization, server push, header compression, and HTTP 2 automatic upgrades. Okay? And there's two variants of this. One is called ALPN, and the other one is HTTP 101, switching protocols. So let's take a look at each of these fundamentally and see what they mean. The first one, as I mentioned, and the most important change in HTTP by far, is the fact that connections are now basically multiplexed. Okay, so we've broken the assumption that a single connection equals a single request equals a single frame. Instead, a single connection now translates to multiple streams, okay? And you should think of each stream as essentially a transaction, a request and response cycle. Okay, a pair of a request and a response constitutes essentially a stream. Within each stream is a message. So a message is a single action, a request or a response. And that message can even be farther broken into frames. Okay, so small parts of an individual message. And by doing this, what we're essentially doing is allowing our connection to be shared in a parallel fashion, much like this picture here. All right? So this is the fundamental building block of multiplexing in HTTP 1.1. A single connection between the client and the server for one single web page, and a pipeline of communication that is multiplexed. So backwards and forward, you have multiple packets at the fundamental level, multiple packets being exchanged, representing multiple streams, all right, across this client and the server. Another important optimization that was made in HTTP 1.1 is something called HTTP header compression, and this bears a little bit of explanation as well. So let's think back again about the old school or the current way of the way client and server interact. Right? So you're you're making multiple requests, all to the same server, generally to the same application. And within each of those requests today, you're actually making HTTP header requests. Each of those requests have a request and a response header. Well, guess what? Because there's so little difference between one resource and the other, most of the time you're actually exchanging the same set of headers over and over again. All right? So let's take a look at an example of request 1 and request 2 in this case. Right? So these are requests to get two different JPEG images. Okay? So the JPEG image, the accept header is the same, the method is the same, The scheme is the same, the host name is the same, the user agent is the same, and a whole bunch of other such information, header information, both on the request and response cycle, are all duplicated across each request. So now that we have a stateful mechanism between the client and the server, instead of duplicating these headers over and over again, what you can choose to do is have a caching table, a simple lookup table, both on the client and the server side. And both the client and the server can keep track of what actually changed, right? So on the first request, I've sent out all of these headers. On my subsequent request, the only thing that I actually really need to change is simply the path, okay? The rest of it is all the same. And the client and the server can track this now. So on subsequent requests, they can simply exchange a single header. Okay? So you can imagine how much this is going to cut down on the amount of data that you need to pass back and forth. The third change in HTTP 2.0 is something called stream prioritization. And this is basically to solve the head-of-line blocking problem. So first of all, the head-of-line blocking problem no longer exists, right? Because everything is in parallel. It's no longer in sequence. And there is no de facto notion of ordering per se, right? In the sense that something must be served before something else. However, what there is, though, is some loose notion of ordering, in particular, something called priorities. Now, you might want to ask, well, why do you need this priority thing anyway? Okay, and so let's take a step back and try to understand this. So let's say for a second that you have 3 different resources that you need to load, or rather 4 different resources, A, B, C, and D, okay? On a web page, and on the server side, you know a few things. First of all, you know that some resources are more important than other resources. So for example, you could load a page without loading, let's say, a given image. It's not that important. Or a video that doesn't need to load right away when the page loads. On the other hand, you also know which resource is more expensive to load. Right? So a large video file is going to be more expensive to load than some simple, let's say, a small CSS file. So you can have a negotiation chain between the client and the server that says, okay, not only am I going to give you these resources are actually assigned specific priorities as well. And what this allows us to do is actually load things in sensible orders. Okay? So in the first example, if A is a resource that depends on B and C, and B has a weight of 4, or a priority of 4, and C has a priority of 12, well, guess what? The browser and server are going to attempt to load resource C first. All right? Similar examples all across the board. If you have nested dependencies, it's going to work exactly the same way. And this basically, fundamentally, is allowing you to load resources a bit faster and to use your network traffic in the most sensible way possible, just by some simple negotiation between the client and the server. Finally, there's another interesting problem that isn't solved in all of the prior solutions. Namely, what happens in the actual interaction, right? So if you did nothing else, and you simply said, okay, we're going to multiplex our connections, and we're going to do things in parallel, well, that's fine. The fundamental problem still remains that the browser will need to make that initial connection and get the index.html, and it cannot do anything until it finishes parsing that index.html. Okay? And to make matters worse, let's say we navigate from index.html naturally to some other redirect to index2.html, and then you have to go through that cycle once again, albeit in a prioritized, highly optimized fashion. So can you improve this? And the answer is yes. The reason we can improve this is because of the fact that the server knows what the resource dependencies are. So when you as a developer you are writing index.html, well, guess what? You know that index.html depends on image A, B, C, and script XYZ, right? So what you can do is something called server push, all right? And what server push does is that when you, as a browser, are requesting index.html, the server knows that index.html really means loading these other 5 resources. So instead of waiting for the browser to parse and figure out that fact, the server simply serves up those requests all at once. Okay? And what this helps us do is basically speed up the load cycle even more. So there is no parsing necessary. When it comes time for the browser to parse anything, it already has those resources in cache, even for subsequent requests. Now finally, there's the question of what happens. How do you handle situations where you have an old browser, okay, that is HTTP, does not understand HTTP 1.1, and that browser is making a request to a server that understands HTTP 2.0, and that server also simultaneously serves another browser that does speak HTTP 2.0. So there has to be some way of negotiation back and forth between the client and the server as to whether they're going to speak HTTP 1.1 or HTTP 2.0. And the clever way that this is handled is by simply assuming by default that the connection is always going to be HTTP 1.1. So the server always assumes that I'm going to receive HTTP 1.1 calls, unless the client tells me something different. All right? And that's basically where the HTTP upgrade comes into play. Right? So now the client will say, I'm making a request, server, don't make any assumptions. But at some point in time, I'm going to tell you, yes, I want to upgrade to HTTP 2.0, and only then does things flip over into the HTTP 2.0 world. And it works basically essentially the same way. It all works on port 80 still. And in terms of secure connections though, by default, it's actually using yet another protocol to do this negotiation called ALPN, or Application Layer Protocol Negotiation. So, without further ado, I think the simplest thing I can do is show you this in action. And that's the best way of understanding what HTTP 2 actually gives us. So let me run this demo here. And for some reason I'm having trouble with my mouse. Okay, let me just open up a browser and do it this way. Good, we have a super slow connection, so I can actually show you this exactly the way it is. So let's assume that on the left-hand side of the equation here, you have a traditional request being made to a server. Okay, that's an HTTP 1.1 connection. And this is actually loading a series of images to make this big composite image. So let me do a refresh and show you how that performs. Okay, not sure what that is. All right, so you saw how that was happening, right? It's a little bit choppy, and it took about 1.33 seconds, okay, to load this, which is really good because it's a slow connection, so you'll be able to see the speed difference right away. Now let me run the same thing using HTTP 2.0. Okay, you saw a noticeable difference there. And in fact, this is not just this one demo. So they did a bit of analysis and benchmarking between HTTP 1.0 and HTTP 2.0, and the numbers are actually quite impressive. On average, if you look at a website like, let's say, CNN.com, the orders of perceived performance improvement is actually something like tenfold, right? And really nothing is changing. All you're really doing is you're switching protocols on the browser, saying that we're making an HTTP 2 request as opposed to an HTTP 1.1 request. All right, so here's the good news. The good news is, beyond attending the past 20 minutes or so, you don't need to know any of this. Really, you don't. The reason you don't need to know any of this is because all of this is hidden under the details of the servlet API. We have this really brilliant API that's almost accidentally future-proof. And I'll talk to you a little bit about why that is. And obviously some of it has to do with the design of HTTP 2.0 itself, right? So this was the intent, is to enable these sorts of changes without necessarily forcing a lot of overhead and a lot of refactoring on the application developers end. And in fact, in terms of the APIs end. The good news, in fact, is such that a majority of these changes are actually completely transparent to you. There's actually just one change that entailed an API-level change in the Servlet 4 API. Okay. So how did this happen? How did we manage to happen, and what is the basic thing that is broken? Now let's step back a second. We've all seen the Servlet API, right? It is basically a request-response-based API. There's a service method, there's a do-get method, and the basic assumption there is that you're making a single request and receiving a single response back. How do you now fit this into a world where there is multiple requests happening? Well, the answer is very simple, by applying a bit of illusion and by applying abstractions. So what the Servlet API actually does is that under the hood, at the protocol layer, it actually is breaking down the request-response cycle using a single connection. But you, as an API developer, do not need to be exposed to this fact, right? As far as you're concerned, you are still being given a request and producing a response. Under the hood, that response is simply being made in parallel without you knowing about it, using the same connection without you knowing about it. So this is the little bit of magic trick that happens of why we actually do not need to fundamentally break the Servlet API in order to adapt HTTP 2.0. And in fact, there's only one change, as I mentioned, only one change, API change that you actually need to be exposed to. And that is server push. Okay? All of these rest of these things, request-response multiplexing, binary framing, stream prioritization, header compression, ALPN negotiation, all of these things are actually happening at the protocol level, way under the hood of the Servlet engine. You are not exposed to any of that at all. So the one thing, though, that you absolutely have to be exposed to is the push part, because that's where you will actually be telling the browser, when you make a request for resource A, you also need to load up all of these other dependent resources with that single request. The other change that actually is surfaced at the Servlet API level is this one-on-one switching protocols. But luckily, even this is handled at the protocol layer. And in fact, this particular change is very deep in the Servlet SPI. Right? And this change was actually made during the WebSocket support. The WebSocket support was done in Java 7. So this change was actually already in place. You can take a look at it, and you can change that. You can look at the low-level bowel details of Servlet 3.1, and you'll see the change for one-on-one switching protocols. Okay. So the basic fundamental building block, if you were to look at Servlet for its own sake, is that HTTP 2 is required. And this is a fundamentally important change. And I want you to think about it for a second. So let's assume for a second that you didn't have this thing called Servlet 4. Could you add HTTP 2 support in the Java ecosystem? The answer is you could, but not in a reliable fashion. That HTTP 2 required is a very simple sentence to put up on the screen. But under the hood, what this actually means is that the Servlet 4 TCK, or compatibility test kit, actually now includes a large number of tests to make sure that a Servlet 4 compatible Servlet container actually implements HTTP 2.0. There's actually no other such mechanism to do that other than running the Servlet 4 TCK, right? So fundamentally important thing, because we have so many different implementations of containers, the only guarantee that we actually have that something properly implements HTTP 2.0 in a server, in a Java ecosystem, is by making sure that yes, it does pass the Servlet 4 TCK, okay? In addition to that, there's one more API change that I'll talk about, using the HTTP server push, and even that is actually done in a relatively clean and relatively well segmented way, principally using the Builder API. Okay, and I'll also talk about where is this actually applicable. So this is how the HTTP push API actually looks like. Okay, it's just added a new method added to the HTTP servlet request. Okay, so you'll have to visualize this for a second. So you're receiving an HTTP request. Okay, and within this HTTP request, in your doGet method, you're serving that HTTP request. As a part of that request response cycle processing, what you can do is use the push builder API to say, hey, when you load this resource, by the way, you also need to load these other resources. And what you can do is simply use the builder API to construct your entire dependency chain, right? So you add multiple paths, and you keep, when you're finally done with your entire dependency chain, you finally call push, okay? And that's actually what's going to enact the server push from the server side to the client side. Putting this in a simple state diagram, this is how it will look like. So we get a request for index.html. It's a servlet.service method is invoked, or doGet method is invoked. You get a handle to the request.push builder. You set a path and say push. You set another path for another dependency and say push. And all of these are essentially builder paths. You continually chain these invocations. But what actually happens under the hood is that these are not sent in a unit fashion, in a sequential fashion. You are constructing it in a sequential fashion, but under the hood, the servlet engine is actually processing these through a single connection, typically in a multi-threaded parallel fashion. Okay, so here's a simple example of this, and this actually goes to talking about what are the actual use cases of this push API. In all reality, most of us are not writing servlets. Anyone writing servlets? No, you are? Okay. Congratulations to you. But if you happen to be writing servlets, yes, you will be a consumer of this HTTP push builder API. But the reality is that most of us these days are not using the HTTP, the servlet API natively. We are using it as a foundational building block for other frameworks, other higher level web frameworks. And luckily, these web frameworks actually have a way of knowing these dependencies as well. In fact, in JSF, you know that extremely well, because JSF, in JSF 2.1, introduced the notion of resources. So for a given JSF page or a JSF application, you can actually specify a set of resources. So what these higher order applications can now do is that understand those resources, and without you, the developer, having to do much of anything else, make these HTTP push things happen essentially behind the scenes for you. So this is actually the actual code in the JSF Faces servlet implementation to actually implement HTTP 2.0. This is, if you look into Glassfish, this is the exact code that you will see. And under the hood is just doing exactly what you would expect. It's just iterating through all of the resources for a given URL, okay, and constructing those path parameters and doing pushes. Okay, so the good news is you can actually try all of this out. Java 8 was released actually just before Java 1 of this year, so just a few weeks ago actually. Glassfish 5 actually implements, it's the first implementation of Servlet 4, and I think probably the only production-ready implementation so far. I think Tomcat and Jetty are also very close in terms of, I think very soon they'll implement the Servlet 4 TCK as well. But right now you can go and download Java 8 and Glassfish 5, and you'll actually be able to test out how Servlet 4 and HTTP looks like in action. And I hope you're going to go ahead and do that. Okay, so again, to summarize, HTTP 2 is a long time coming. I think we can all benefit from it. There's a great amount of benefit that all Java applications can get out of HTTP 2 and Servlet 4. Basically, Servlet 4 is the principal vehicle by which HTTP 2 support is being added for the entire Java ecosystem. Whether or not you're using Servlet API, these servlets are being used under the hood by your web application, and that's all going to take advantage of HTTP2. And of course, you can now try it out, okay, using at least Glassfish 5 for now. Okay, so a few resources that I have to share with you, not a lot. The first one is the serverless spec itself, and obviously the Glassfish URL, glassfish.org URL. But a lot of what I actually explained to you, I read myself. There's a very nice resource out there that explains step by step what the HTTP2 protocol is actually about. So that's the URL for that over there, and I hope you'll get to take a look at it when you get a chance. Okay, so I have about 15 minutes or so. I will like to actually finish early. I know we're quite late in the cycle in terms of our opening ceremonies and the like, so if you don't have any questions, feel free to leave. But if you do have some questions, I'll take some questions now. Any questions? Yes, sir? So I'll repeat the question. So this is actually a very legitimate question. So the question is, how do you now debug HTTP 2.0, right? So if you ever debugged HTTP 1.0, how do you do it? With a bit more than a browser, perhaps something like Wireshark, right? Something like Wireshark, because it's all essentially plain text communication. You can see the request and response cycles exactly. Okay, and it's very easy to track because it's a distinct connection being made, and you can read out what the request and response cycles are for those requests and responses in HTTP 1.0 world, and that is actually intentional. Okay, so that is one of the design intents of HTTP 1.1 is that simplicity and being able to debug that. Now, and it is true that in HTTP 2.0, you're not going to get away with very simple tools. It's not going to be so easy to debug anymore, because now when you open up a Wireshark, if Wireshark didn't do anything, okay, and continue to do what it does today, what you will see is gibberish, right? Because these are binary frames. They're no longer ASCII interactions at all, and they are interlaced with each other. Okay, so it's not like it's a single stream that you can take a look to decipher what it means. These messages are intermingled. So what do you do? The answer to the question is that yes, debugging is going to be harder. We hope that it's going to be worth it, okay, because we're going to get this performance benefits. And the good news is that browsers and Wireshark actually have been re-engineered to handle this situation. Right? So if you look at browsers that support HTTP 2.0, or you look at Wireshark now, Wireshark will actually do the work of segmenting out your streams. So you can actually see distinct streams just the same way you would, and it actually where possible, it also does the binary decoding. So you're able to see the message in text format just the way you would before. But yeah, if you open up a browser that doesn't have those enhancements, or you're just opening up a TCP socket, you're just going to see gibberish now. Okay. Any other questions? Very good question, by the way. Any other questions on HTTP 2.0? No? Nobody? Yes, sir. A bit louder, please. You're loading a page, and something breaks. I see. Yes. Okay, yeah, this is basically a problem too. You have to have more intelligent browsers and servers that can basically recover from that. But I think in this situation, my guess is that when connection breaks, you probably will just have to abandon the transaction altogether and restart it, because it's just everything is intermixed together. So that's a good point as well. Okay. Any other questions? Yes, sir. Very good question again, right? So this is a very real problem. So here, there's good news and bad news situations. The good news is that the fundamental API protocol hasn't changed. So it still looks like over-the-wire communication between a client and a server. It's still using the exact same ports, so port 80 for HTTP and 443 for SSL and secure connections. So from the perspective of a firewall that doesn't care about the content of your HTTP request, it looks very much the same. Right? It just looks like, okay, there's a browser and a server talking HTTP protocol over these known ports. Now, if you have a very intelligent firewall that actually cares about the contents, okay, of the HTTP connection as to what is being exchanged, then yes, that will have to be retrofitted to actually recognize and be able to decipher what is actually being exchanged. Okay. Any other questions?
Yeah. If our resource depends on some external resource, for example, some external URL.
Yes, external URLs there's no way to handle. So if the assumption of all of those assumptions of optimizations, they're geared towards a single browser and a single server. So the connection reuse, the compression, the prioritization, those all hold as long as it's a single server and a single browser, a single server. If it's multiple servers, those are essentially treated as two separate cases.
This is clear, but is there a way to define this dependency? I mean,
Not that I know. No. So the question is there any way to say that, okay, these are two different servers, two different subdomains, but they're really one logical server? Not that I know of. Subdomains would be treated as different servers, essentially.
And how do we prioritize this?
You won't be able to again. So again, it would have to be the single server that's talking to a single browser, and then prioritizing that stream. So if it's another server, it would be counted as yet another connection altogether, with its own priorities. Okay. Same answer. Yeah. So again, to a transparent proxy, it just looks like plain old HTTP over the same ports. If the proxy server cares about the actual content, then yes, it would have to be explicitly HTTP2 compatible. So what's server push is not simply a matter of what the server does, it's also about what the browser does. When you actually perform a server push, the assumption is actually that the browser will cache that resource, right? So here's how the interaction would actually look like. A browser makes a request for a resource, let's say index.html, and it includes your video. On the server side, you're going to say, okay, I'm going to send this video and the index.html at the same time before the browser parses it. The assumption is that the browser is going to cache both the index.html as well as the video. So when the browser actually gets to that request and it says, okay, I need this video, and it goes to make the subsequent request, it will actually already see that I already have the video cached. Exactly. So the resource is being sent to you from the server beforehand. The browser is caching that for that particular interaction, so that when it actually gets to actually using the resource, it already has that resource in its cache. So you would handle that via priorities. So you can set the video priority to be lower, and that would be a hint to the browser that is, I don't need to render this video before I render the page. Okay. All right, any other questions? And I think I have 5 more minutes or so. Okay, any other questions? No? All right, excellent. So I'll be around. Thank you very much. I'll give you 5 minutes back for what it does for.